In the previous section, we defined addition and subtraction between two vectors. In this section, we will learn one kind of the product between two vectors. Say we have two vectors. Vector A, which is a triple, A1, A2, A3, and a vector B, B1, B2, and B3. Now we define a dot product between two vectors as this way. Is A1 times B1 plus A2 times B2 plus A3 times B3. Okay. So as a result, is a scalar. Okay. So I really want to emphasize that the dot product of the two vectors is a scalar. Okay. Now I refer to the book for the properties of the dot product. For example, A dot product itself give you A1 square plus A2 square plus A3 square, which exactly is magnitude of A square. Okay. And also you can check that A dot product B is equal to B dot product A, which is not hard to check. Okay, if vector A is like this, B is like this, and we called theta is the angle between vector A and vector B. Then we have a formula. A dot B can be calculated by the magnitude of A, the magnitude of B, times cosine theta. Okay. Magnitude of A is this length of your vector. I refer to the book for the derivation for such a formula. Okay, this formula also can be written as cosine theta equal to dot product A and B and divided by its magnitude. Okay, using this formula, you can find the angle between two given vectors. Okay, now let's look at an example. Okay. Now I give you two vectors. U there is I minus j plus 2k. And I give you another vector v. V here is 2i minus j. I put an arrow on the top, just means it's a vector, plus k. And this vector also can be written as a triple. 1 minus 1 and 2. I think this way is easier to write. 2 minus 1 and 1. Okay, now that means I give you two vectors. One is u, one is v. Okay, I want you to tell me, are those two vectors orthogonal to each other, or parallel, or neither? Okay. How can we tell that? If the angle between u and v, theta is 90 degrees, we say they orthogonal, or we say perpendicular, the same thing. Perpendicular means orthogonal. They are like this way, okay, 90 degrees. Or u is like this, u and v have the same direction. Then we say parallel. They have opposite. If u is here, v is here. Okay, they're also parallel, but with the opposite direction. Okay. So those things can be told by the angle between them. So what we need to do, just using this formula, A dot B, magnitude of A and the magnitude of B. Okay, first of all, let's find dot product between A and B. By definition, is 1 times 2 plus minus 1 times minus 1, then plus 2 times 1. So give us 2 plus 2 plus 1, give us 5, right? Okay. Then we need to find the magnitude of A, which is square root 1 square plus minus 1 square plus 2 square, which give you square roots 4 plus 1 give you 6. Similarly, we can find the magnitude of B. Okay, B is a vector with a 3 component. Magnitude of B is a scalar. So magnitude of B is 2 square plus minus 1 square plus 1 square give you square root of 6. So cosine theta is equal to square root of 6, and this is 5. So 5 over 6. So what is the conclusion we can make? Say the angle between U and V. Are they perpendicular? What do we mean perpendicular? That means if theta equal to 90 degree, right, or pi over 2, then U and V perpendicular, we'll use this notation. Okay, if theta is 90 degree, which also means what? Cosine 90 degree, which is 0, okay. Do we get a 0 there? No. So they're not perpendicular, okay. Are they parallel? What do we mean parallel? Parallel means either U and V same direction. If U and V same direction, that means theta is 0 degree. Okay. If theta is 0, implies cosine 0 is 1. Okay. Now what we have is what? 5 over 6. So it's not 1. Another situation, U and V parallel, that means theta equal to pi. Okay. U is here, V is this. They're parallel. However, okay, if theta equal to pi, then cosine pi give you minus 1, which is not 5 over 6 neither. So the conclusion is what? U and V, that they're not perpendicular, they're not parallel neither. Okay, as I said before, you can define the multiplication, what we say the product between the two vectors, as any way you like. Why we define a dot product like this way? Because we can find many applications in the real life. For example, in the physics, if for the W denote for the work, okay, work has been done by the force, which is a vector, dot the displacement, which is another vector. Okay. That's the formula for the work has been done. Okay. Then we use the dot product. Let me give you an example. Say you have a little card here, and you have force here, and your card go this way. Okay, this is a displacement. Okay. Now this force can be decomposed to the two. Okay. One is called F1, which is the same direction as D. Another is F2. Okay. Obviously, F2 make no one of the component of force F2 make no contribution for the displacement. Makes no contribution, does no work. Okay, the work has been done is really totally by F1. F2 is balanced with the gravitational force. Keep this card stay on the ground. Okay, so by this work is F dot D, and by the formula, this is the magnitude of D times the magnitude of F, then times cosine theta. Theta is angle between F and displacement D. Now let's look, what is this? Magnitude of F times cosine theta. That's exactly is the magnitude of F1. Why? Look at this right triangle. Okay. Look at this right triangle. Cosine theta is equal to adjacent side, which is the magnitude of F1. Wait. Magnitude adjacent side, magnitude of F1 over hypotenuse. This is the magnitude of the length of that, the magnitude of F. There's no one here. Okay. So therefore, the magnitude of F1 is cosine theta times magnitude of F. That's why the magnitude of F1, which is really the work of the force make a contribution for this displacement. So that's why the dot product is very useful. So from this application, we can tell in the real world, there's such need to find F1. We need to find F1, which is a vector, and we also need to find F1 is a magnitude. Okay, see, that's what I underline here. The magnitude of F1 give you the force make the work, which means move this card. Okay. So that's this sense. That's what we're going to see. We call the scalar product of F on D. Okay, and this vector we called vector projection of F project on D. We'll have two definitions. They call the scalar projection. They use this notation. This means project B on vector A can be defined by dot product of those two over the magnitude of A. This really is like the magnitude of F1. Then we'll have vector projection. They use a notation like this. Project B, vector B on A can be calculated by A dot, the dot product of those two over A square, then times A. So now let's look at this. F1 is one of the components of F. F1 have the same direction with D. So pay attention here. Scalar projection is a scalar. Okay, result is a scalar, which give you magnitude. The vector projection give you vector. This whole thing here is a scalar. Okay, then a scalar times a vector A still give you vector. The scalar projection. Okay, now let's see what is a scalar projection means. Say this is vector B, this is vector A. and the theta is the angle in between. Okay. Remember, what we're interested is make this 90 degree. Okay. We want to find this length. This length really is what we call the scalar projection. How do you find that? If I call this length here x, remember cosine theta, this right triangle is adjacent side over the hypotenuse, which is the magnitude of b. It's not just b, okay? It's the magnitude of that. Remember, b is a vector with 3 components. So therefore, your x there is equal to magnitude of b over cosine theta. Okay, what is cosine theta? The formula for that is a dot b over magnitude of a and the magnitude of b. You cancel the b here, give you a dot b over the magnitude of a. So I really hope my students say find the scalar projection of b on a. I just don't want you to just say give me 6 number. I just plug in, just make some computation, and I don't know, and you don't know what you get for. Okay, this really project your b on a, and the scalar projection give you the length of that. They could be negative number. Okay, what is the vector projection? Vector projection give you this vector. So how do you find this vector? If I call this vector a, b, I call this vector d. Okay, you see, you know what I mean. This is my vector. So first of all, my vector d and the vector a, they're what? They're parallel, right? So they can be written like this. Whenever 2 vectors they're parallel, they can be written, one is scalar multiplied in the other one. Okay. And we know the magnitude of that was, maybe with a sign. The magnitude of that is a dot b over a. Okay. So we take c like that. Then, okay, whenever you see anything like this, what do we mean by that? This means this is a scalar, okay, times a vector. So this whole thing, scalar times a vector, that means this whole thing has a vector of same direction as a, but with a different magnitude. And if you divide it by its own magnitude, then this whole thing's magnitude is 1. So this thing is the vector of same direction with a, but the magnitude is 1. So the magnitude is determined by this. So that's what we have this formula. A dot b over the magnitude of a square and a. Okay. Remember, the vector projection is a vector. This thing is a scalar. Okay. And this one have the application, as I told you, for example, to find the work.